Um, okay. So, Catalina, if you can start with Tony here, that'd be great. And then we can hand off the mic from there.
Hi, good morning, everybody. My name is Tony Quiros, and I'm the Water Resources Planning and Management Analyst here at the Coachella Valley Water District. Thanks for having me.
Ryan Sullivan. I'm with PGA West. Am I supposed to? With PGA West and with my friends here from California Turf and Landscape Foundation and the California Alliance for Golf.
Thanks for joining us.
Good morning, everyone. I'm Joanne Lay, Director of Environmental Services for the Coachella Valley Water District. Welcome.
Morning, everyone. Levi Anderson. I'm Senior Environmental Compliance Specialist here at CVWD. Welcome. Glad to be here.
Good morning, everyone. Sarah Rapola, Water Resources Manager at Desert Water Agency.
Hi, good morning, everyone. I'm Jennifer Salazar. I'm the Water Resources Specialist at Desert Water Agency. Welcome.
Okay, so I think those are the partnering agencies we have here in person. Of course, we have a couple of folks online. But for the time being, I will hand it over to our consulting team who's going to be covering work previously done for the SNMP, as well as our most recent efforts with Task 5, which is a development use of forecasting tools in this plan. So thank you, and thanks for being here.
Okay. Here's our plan. Because it's been a while, we're going to do a very fast refresher on the who, what, why, how of the CV-SNMP and a quick overview of technical memorandums 1 through 4. Our primary focus for this community workshop is number 5, construct nitrates, total dissolved solids, forecasting tools, woo, animations, and evaluate the baseline scenario. So really, really cool stuff is happening. I was talking to Kevin and Craig in the lobby, and they're like, no wonder it took a while. It was 900 pages long. So we're going to do our best to show you what the 900 pages contain. And then, of course, we'll talk about next steps, give you some other options to share your comments and thoughts with us and how you can stay involved. And then we'll keep talking, open discussion session. Okay, we're not sure about if this poll is going to work because you may not have cell phone service in here, but we thought it would be fun and interesting just to say, hey, who's tracking along with us today? Which category best fits you in this groundwater basin? I think it's actually set to select up to 2. I have 0 cell phone service in here, so the poll did not work for me. If you're joining us online, you can either scan the QR code or you can go to slido.com and put in this number 1997341. Maybe, Carol, if you pull it up, then you can see the responses as they come in live. Sadly, we weren't able to integrate the live polling technology into our slide deck because of some firewalls, but it was cool, I promise. How's it looking? I mean, obviously we've got some water users, we've got some golf industry folks, we've got government.
Yep, government agency 80%.
80%.
And we have other interested party, which may just be me.
Yeah, well, at least one person is another interested party. We're testing to make sure we're connecting with the right folks. And we're very happy you all are with us today. All right, let's get going. I'd like to welcome to the stage Andy Malone. Oh, and also I forgot to mention, we don't have a camera available for us in the boardroom today. Usually you're able to see us. So sorry, but everyone looks very nice.
Thank you, Megan, and good morning, everyone. For those of you who don't know me, I'm Andy Malone. I'm a geologist with West Yost Associates, and I've been leading the technical effort to develop the salt nutrient management plan with a lot of help from Carolina Sanchez here and our water quality and modeling teams at West Yost. Just want to remind everybody today is all about education, so I really do encourage you to raise your hand and speak up if you have a question as we go along here. We do have a website, and it's shown up here on the screen. Encourage you to visit the website if you want to see any of these technical materials that we're going through here today. This is the central place where we're posting everything. So I'm going to go through some of these what's and whys and how's we're developing the salt nutrient management plan. You see the acronym up there, CV-SNMP, and that stands for Coachella Valley Salt Nutrient Management Plan. It is meant to be a basin-wide plan to manage salts and nutrients in compliance with the state's recycled water policy. We have links to the recycled water policy on our website as well as the state's websites. Recycled water policy recognizes that just going through the normal use of a groundwater basin, including the use of recycled water, can lead to accumulations of salts and nutrients in the groundwater basin, which over time can affect the uses, adversely impacting the uses of the groundwater basin. And so the intent of a salt nutrient management plan is to manage salt nutrient loading such that those uses of the groundwater basin remain protected today and out into the future for future generations. Why is this important? Because the whole economy out here in the Coachella Valley is tied to water. We're living in a desert out here, and water is what makes everything run. This management plan has the potential to affect our ability to use recycled water. Recycled water is increasingly becoming an important water resource in the portfolio out here in the Coachella Valley. And so this plan could impact the ability to use recycled water. Could also impact the ability to use Colorado River water. Colorado River water is an extremely important source to sustainably manage the groundwater levels in the basin. So it's extremely important, and we use it in a big way to artificially recharge the groundwater basin. It could also affect the way we manage and treat our water and our wastewater in the Coachella Valley, which will have cost implications, which will cascade down into consumer water rates. So this plan is very important in many different ways to the valley. Our goals are to manage salt and nutrients in a way that makes sense. Where and when it needs to be managed needs to be identified and needs to be planned for in the future. We want to do this in the most efficient way possible so we preserve the affordable use of water in the valley. And then most importantly, we need to protect groundwater quality, these uses of groundwater for future generations as well as today. Okay, who's involved in the development of this plan? I'm going to start at the top and go left to right, and then across the bottom. We'll start with our steering committee. These are the water and the wastewater agencies that are being required to develop this salt and nutrient management plan. They are the ones that are funding the development of the management plan. They're the ones that are conducting the monitoring programs. You'll see some of the data today. And so they are leading and supervising the development of the plan. They have also formed a technical advisory committee, which consists of experts, hydrogeologists and water quality experts that are involved with the development of the sustainable groundwater management plans in the valley, and as well as a third consultant that's independent and has experience in salt nutrient management in the Central Valley. So this is a technical advisory committee that is periodically reviewing our interim work products and providing us advice along the way. When I say us, I mean the consultant team. Megan here is a part of our team. She is in charge of public outreach. We also have a legal and policy advisor. Her name is Tess Dunham. She's not here today, but she's obviously an important component of our team. And then West Yost is the technical consultants that are conducting the groundwater modeling and developing the plan that we'll be talking about today. The regional board, we have a number of representatives from the regional board. They're the main state regulator for water quality, and in this region, they're called the Colorado Regional Board. And so they will ultimately need to take this plan and adopt it and potentially incorporate it into their water quality control plan. Sometimes we call that the basin plan. So they are also a stakeholder and have been involved all along the way, as we'll talk today, approving the work plan to develop the salt nutrient management plan, as well as commenting on all of our interim work products. The Native American tribes of the Coachella Valley are also an important stakeholder. We've been keeping them informed of our progress as we're going along, and they have been submitting comments on our interim work products along the way too. So they're staying informed. Not every tribe in the valley, but some of the main ones have been. And then we have our public stakeholders, which include salt and nutrient contributors. Whether or not we know it or not, most of the public here is involved in some way of contributing salts and nutrients to the groundwater basin. And so these public stakeholders can also be impacted by this plan. So it's important to keep the public informed as we go along through this process, because they might also be impacted and maybe even involved in the implementation of the plan. So I mentioned our work plan. To talk about how we've gone about doing this, a little bit of background. In 2021, we developed a work plan, which is the roadmap to our technical approach and our schedule to prepare the SNMP. West Yost has been conducting the technical work. It's been guided by the steering committee. We have our input from our TAC, or our technical advisory committee. And then we have these draft work products that we develop that then we publish and try to receive input and maybe modify those interim work products into final work products by circulating them through not only the TAC, but the regional board and the public as well. Real high level scope of work. So it's obviously more involved than what we have on the screen here, but generally the way we're conducting this work to develop the plan is, first of all, we attempt to characterize what current groundwater quality looks like in the basin, as well as all the sources of salt nutrient loading. And I probably should stop here and give a little bit of detail on the precise contaminants of concern that we are addressing here. One is total dissolved solids. That is a measure of the salinity of the groundwater. It's measured in milligrams per liter. We sometimes refer to total dissolved solids as TDS, but it's basically the salt. One component of that salt is nitrate, and that is a nutrient. And so nitrate is nitrogen and oxygen, and it has health effects. And so we segment it out separately as a nutrient that we're concerned about in terms of managing in the groundwater basin. So TDS and nitrate are really what we're talking about in terms of the constituents of concern. And so our first step is to characterize what TDS and nitrate look like across the basin, not only spatially, but depth specifically. So we're also looking at depth here as well. And then all the sources of salt nutrient loading, which there are many, and we'll review some of those here today. What we then set off to do is to identify how groundwater is being used across the basin, where and how groundwater is being used. And each use might have a different TDS and nitrate threshold, which might, if you increase concentrations above those thresholds, it might impact the use of the groundwater. So what we attempt to do in this next step here is not only characterize how groundwater is being used, but then what are those TDS and nitrate thresholds that we don't want to cross over for fear of adversely impacting those groundwater uses. The next step is then to take a look at the future, and we do that with computer simulation models of the groundwater basin. And we look at the water supply plans and the wastewater disposal plans in the basin, and we attempt to simulate how TDS and nitrate concentrations in the groundwater basin will change over time, and whether or not we're predicting to see impacts to the groundwater uses in the groundwater basin. That's going to be the lion's share of our discussion today, is our computer simulation models and our predictions of where we see TDS and nitrate concentrations going in the groundwater basin. And then our last step is to collectively use all of this information that we learn and prepare a groundwater management plan or a salt nutrient management plan for the Coachella Valley. High level, it's broken down actually into many more different specific tasks. For each task, as we go through it, we have a review process where we first of all prepare a TM, and TM stands for Technical Memorandum. So the memorandum describes the objectives and the methods and the results and conclusions and any recommendations we have out of completing that task. And we run that memorandum in draft format by our steering committee, and we get input back from the steering committee, and then use that input to prepare an administrative draft of that TM. And then we present it to the technical advisory committee, and they give us their input, and we actually document their input and then our responses to their input. Sometimes our responses cause us to change the memorandum. But we document that into the TM as an appendix. And then we send the TM out for public review, and we receive public feedback, including feedback from the regional board. And we do the same thing. We document that feedback and our responses to that feedback. And that becomes a final TM. All these TMs get combined at the very end of our study, which should be happening within the year, to prepare the final report on the SNMP. We started this effort back in 2022. We're hoping to be complete by the spring or the summer of 2027. So we have about 9 months left. This chart here shows you our schedule in a little different way, a little more detailed in terms of our specific tasks. And so we are actually up here at this yellow milestone marker here, which represents the public workshop that we're having today, where we are discussing the construction of our computer simulation forecasting tools and our evaluation of our so-called baseline scenario. And our next steps are to develop salt and nutrient management scenarios and run them through our computer simulation models, look at the costs associated with those scenarios, and with that information here, develop our final salt nutrient management plan. We will be combining these two workshops for task 6 and task 7, where we're looking at potential salt nutrient management scenarios or strategies and the costs associated with them. We're going to have another public workshop where we combine the results and recommendations coming out of these two tasks. One of those recommendations will be, what do we want our salt nutrient management plan to be before we document it in the report in task 8. In terms of what we've completed, our TMs1, where we characterized loading, and TM2, where we characterize current groundwater quality, those are complete. We are just working on some language comments from the regional board on our task memorandum number 3. So we're almost complete with that. We have completed TM4, where we described our technical approach to how we're going to develop these computer simulation models to forecast water quality. That's been complete. And we are about 95% complete with our TM5, where we've constructed the tools and we've run this baseline scenario to simulate the future. That TM is now out for public review, and that's going to be the focus of our discussion at the end of my presentation here. Here we have already begun some of our work on forecasting different strategies for managing salt and nutrient accumulation in the groundwater basin. So we have begun some of our modeling here, and that's why we're showing some substantial percentage of completion here in our TM6, but nothing has been published as of yet. And we have not started our cost analysis of any of this yet. So we've got some work to do here in the future. And so, as Megan mentioned earlier, today's focus, I'm going to give you some of the highlights of where we've been with some of our earlier technical memoranda. And then we're going to discuss in a little bit more detail the results and recommendations coming out of our technical memorandum number 5. So we'll start with TM1, where we characterized loading. What we wanted to do here is develop some understanding of where and how much TDS and nitrate loading was occurring in the groundwater basin. We wanted to understand if there's seasonal variability to it. Are there any trends? Is it increasing? Is it decreasing? We wanted to develop understanding there. And then we could use that understanding to help us develop logical areas of the basin that we call groundwater management zones, where we could manage salt nutrient loading. So it helped us, that understanding of where the loading is occurring helps us better delineate these groundwater management zones. It also helps us in our modeling tasks. We need to understand where and how much loading is occurring so that those can be inputs to our groundwater models. Okay, I'm going to show you a map from TM1 which identifies the location of loading sources. I'm going to spend a little bit of time on this. First, it's super interesting. Second, it's really important to understand in terms of future management strategies. And so This is a map of the Coachella Valley, and my cursor is generally outlining up here the Mission Creek subbasin, the Desert Hot Springs subbasin here, and then the main part of the groundwater basin, which is the Indio subbasin, which stretches all the way from Whitewater all the way down to the Salton Sea. And there's a lot of symbology on this map, and I'm going to go through them one by one because they are important. The first source of salt and nutrient loading are the wastewater percolation ponds that are located across the basin. They are very small on this map because this is a map of a large area, but they occur where we have the red polygons in the basin. So Palm Springs, for example, in this area here, they have some wastewater percolation ponds. The wastewater percolates into the groundwater basin. It could potentially be pumped out in the future. It is a source of loading, even though it occurs in small areas and in limited volumes across the basin. Some wastewater now is being treated and then reused for irrigation. And those areas are shown here as purple outlines, either in municipal areas or for golf course irrigation. So these, at least when we publish this memo, these areas outlined in purple are where recycled water was being used for irrigation. Now, this is a really important point to understand is when you apply water to the ground surface for irrigation, the grasses or the plants use up some of that water, don't really use up much of the salt, but they use up some of the water, and some of the water migrates past the root zone and will infiltrate all the way back to the groundwater in a highly concentrated form. And that is a source of salt and nutrient loading to the groundwater basin. And you'll see from our modeling studies that we are showing that that is an important driver of salt and nutrient accumulation in the basin. It's not only from recycled water, it's from irrigation with groundwater, it's from irrigation with Colorado River water, that any sources of salts and nutrients in water that get applied to the ground can return to the groundwater basin and add salts and nutrients to the groundwater basin. We have septic systems. For those land parcels that are developed that are not connected to the municipal sewer system, many of those, all of them, I would say, that generate wastewater have an on-site wastewater disposal system or a septic system. And those can infiltrate to groundwater and add salts and nutrients to the groundwater basin as well. And so those are shown by the darker brown colors across the basin. We have our groundwater replenishment facilities. The largest, of course, is the Whitewater replenishment facility here at the upgradient, in the upgradient portion of the Indio subbasin, but we have Mission Creek groundwater replenishment facility, Palm Desert, the Thomas Levy. Those are some of the main ones across the basin. And this is where Colorado River water is imported either through this blue line, the Colorado River Aqueduct, which comes up and can discharge to Mission Creek and Whitewater, or the Coachella Canal that can bring water to Palm Desert or the Thomas Levy groundwater replenishment facility. So this is where Colorado River water gets artificially recharged to the basin for sustainability purposes to make sure that our groundwater levels don't continuously decline in an overdraft situation. So really important water source to the region, but Colorado River water has TDS concentrations that are typically above 600 milligrams per liter. So it can be an important source of salt loading in particular. Very low in nitrate, but relatively high in TDS concentrations. And then we have our areas of return flows from outdoor irrigation. In blue represents generally the urbanized areas where we have outdoor urban landscapes where water is used for outdoor irrigation, and we can have return flows from those areas. Golf is a big industry in the valley, and so in yellow are the general locations of the golf courses. They also pump groundwater and use other supplemental supplies to irrigate their golf courses, and you can have return flows from turf irrigation at golf courses that can contribute salts and nutrients to the groundwater basin. And then lastly, we have the agricultural area, the most down gradient portion of the basin, in what we call the Indio East area, and so that's shaded in green here. What's unique about the agricultural area is that the soils in those areas are relatively clay rich. When you irrigate, those shallow soils can become super saturated, which is not good for the crops. And so what's been installed historically have been these tile drains, which can drain some of that irrigation return flows into the channels, which ultimately drain to the Salton Sea. So some of these return flows from irrigation of agricultural areas can be intercepted by these tile drains and then exported and do not flow into the groundwater basin in the volumes that would be without these with these tile drains. So that's a little uniqueness that we consider in our groundwater flow models for the agricultural areas. Any questions on loading? Of course, if you're going to try to simulate how salts and nutrients accumulate in the groundwater basin, you need to understand where your different sources of loading are and how much water is being applied and what the TDS concentrations and nitrate concentrations of those applied waters are. So really important information that we developed as part of TM1. Moving on to TM2, here's where we characterized what current groundwater quality looks like in the groundwater basin, not only spatially, but also depth specifically. So we collected as much data, historical data, that we could. Most of that data comes from groundwater quality samples at wells. So we have knowledge of historical groundwater quality at specific points across the basin. Not a whole lot of data, but we collected as much as we could and characterized it as best we could for a historical period. This information is also really key to helping us delineate our groundwater management zones, as we did in TM3. And then it also provides us with our initial conditions for our computer simulation models. That's key input to a computer simulation model. If you want to project the future, you need to know what the present is so that you have a starting point to make your projections. And then it also, just by understanding where salts and nutrients are loading, and then understanding what the groundwater basin looks like today in terms of its TDS and nitrate concentrations, you can begin to understand how the groundwater basin works, how these loading sources are loading TDS and nitrate to the groundwater basin, how the groundwater is flowing, and eventually, this is what we have today. So it helps us better understand the fate and transport of salt and nutrients in the groundwater basin just by understanding loading sources and what the groundwater basin looks like today. This information of current groundwater quality knowledge can also I touched that on accident. Helps us develop recommendations for TDS objectives, which are not, there are no numeric TDS objectives in the basin plan today. a potential end result here is that the recommendations coming out of this plan may cause a basin plan amendment where TDS objectives are added to the basin plan. So this information is important in that effort. And as well as if the regional board is going to grant assimilative capacity for additional TDS loading, let's say from imported water or recycled water recharge projects, that they have this current understanding of the groundwater basin to help them make that decision on the allocation of assimilative capacity. And from our TM to this, these are some maps here that that are looking at the deepest portions of the aquifer system in 2019. So what you see on the left here are the raw data coming from the wells. So each dot here represents a well, and the size and the color of the dot represents the TDS concentration for right around 2019. And so the blue dots here represent really high quality water with regard to TDS, less than 250 milligrams per liter. That's basically rainwater quality of water. And you can see that there are a lot of blue dots here that are from wells that penetrate deep within the aquifer system. But then you have progressively, as you move from green 250 to 500, yellow 500 to 750, orange 750 to 1,000. This is all still drinkable water, but once you get over 500 milligrams per liter, you begin to notice tastes and odors in the water, and so it's a consumer acceptance threshold, 500 milligrams per liter. But there's no health effects going above 500 to 1,000. Generally, you don't want your water to be over 1,000 or over 2,000. This is bordering then on non-potable water for drinking water purposes. So you can see a few wells out here have higher TDS concentrations, but the lion's share of the wells are still very good quality water that's in the deeper portions of the aquifer that are generally the main portions of the aquifer that are used for groundwater, that the wells use for groundwater pumping. We take these data here and then we interpolate between the wells to generate what we call a raster of groundwater quality with the similar intervals of class intervals here of TDS concentration. We do this because our model spans the entire groundwater basin, and we need to have an initial condition for our model. So we generate these rasters here across the entire groundwater basin. You can see that we generally have this deeper groundwater that is of fairly good quality, generally less than 500 milligrams per liter across the major thickest portions of our aquifer system here in the middle. But then we do have some higher concentrations in areas that have presumably been impacted by agricultural land uses or potentially groundwater that's migrating from beneath the Salton Sea into these areas as wells pump in these areas. We also have some higher concentrations up here in the Mission Creek subbasin. These might be due to some upwelling of thermal waters. We don't really understand it that well, but we know that there is upwelling of saline thermal groundwaters that are very prominent here in the Desert Hot Springs subbasin, but can flow into the Mission Creek subbasin here too, as well as our other loading sources that we talked about earlier. So you'll see a lot of these maps in TM2, not only for this deeper aquifer, but into the shallow aquifers too, which typically when you get to the shallow aquifers, you see higher TDS and nitrate concentrations because these shallow portions of the aquifer system are closer to the loading sources. Okay, moving on to our technical memorandum number 3, where we took this information from TMs 1 and 2 and we used it to delineate our draft groundwater management zones, and then described how water is used in each one of these management zones and the groundwater use thresholds for each of those uses. So that was really our intent from in TM3, was to develop these draft groundwater management zones. We admitted in TM3 that we're taking a shot at developing these management zones. We're going to base them on the hydrogeology, where the faults are, and where the loading sources are, what groundwater quality looks like. We considered it holistically and developed these management zones, but we knew we were going to be doing these computer simulation models of the future, and that this information might cause us to go back to our management zones and redelineate them in ways that best facilitate long-term management of salt nutrient loading. So they're draft right now. It may be that we change them up as we move into TMs 5 and TM6 in the future. This is a map that is derived from our TM3, where what we did was we developed a number of management zones here, and I'll go through them. The first one is the Desert Hot Springs Management Zone, not really used that much in terms of groundwater use, but this is north of the San Andreas Fault, and TDS concentrations here are generally quite high, over 1,000 milligrams per liter for TDS, and then for nitrate, 2.6 milligrams per liter. The maximum contaminant level for nitrate is 10 milligrams per liter, so this is well below that in terms of a drinking water regulatory standard here, but fairly high TDS concentrations in terms of we call it ambient water quality, but it's generally an average TDS concentration across the entire management zone where we have data. If we move here to the Mission Creek groundwater management zone, it is bounded by the 2 splays of the San Andreas Fault, the Banning Fault here and the Mission Creek Fault here. And these faults act as barriers to groundwater flow. So they inhibit groundwater flow from Desert Hot Springs into Mission Creek and from Mission Creek into Indio. That is one of the main reasons why we delineated this management zone separately. The ambient TDS concentration here is 502 milligrams per liter, and just about 1 milligram per liter for nitrate. The next management zone we delineated is the Indio West Management Zone. So it is south of the Banning Fault, and then it is bounded on the west by the San Jacinto Mountains. And it has a ambient TDS concentration of 343 milligrams per liter and about 2 milligrams per liter for nitrate. Generally, we don't have a vertical stratification of the aquifer system here in terms of laterally extensive clay layers that might cause us to treat the Indio West groundwater management zone differently in terms of its vertical stratification. So this area right here of the basin, we consider the entire thickness of the aquifer system as part of the management zone. Same goes for the Mission Creek and the Desert Hot Springs subbasin. But if we move here into the Indio East groundwater management zone, we do have distinct vertical stratification of the aquifer system as well as groundwater quality. It gets worse as you go from deep to shallow in terms of concentrations of TDS and nitrate. The shallowest portion of the aquifer system is really between about 50 and 100 feet below ground surface. And it is this hatched area here, which we call the Indio East Perched Groundwater Management Zone. Isn't really pumped and used for any purpose, but it is an area where the agricultural irrigation has caused a pretty high concentration of TDS and nitrate concentrations, over 2,000 milligrams per liter in terms of TDS, almost 6 milligrams per liter for nitrate. We don't, because it's not really used, we don't have much data on this area. And the agencies are installing new wells to better understand the perched aquifer system here, but generally it's unused. The shallow aquifer system, generally about 100 to maybe 400 feet below ground surface, underlies the perched aquifer system across this whole yellow area here, that's shaded yellow here. Its TDS concentration is about 643 and on average about 2.5 milligrams per liter for the shallow system. But then the deepest system, which again is the most used portion of the aquifer system, the water quality is much better, about 388 milligrams per liter as an ambient concentration and about 1 milligram per liter for nitrate as nitrogen. What we did was we compared these ambient concentrations to these groundwater use thresholds for TDS for these various different uses that occur across the basin. So for domestic, as we were talking earlier, the 500 to 1,000 milligram per liter TDS threshold. For outdoor irrigation at golf courses, about 1,280 milligrams per liter threshold. For industrial, it's 850, and agricultural is very interesting and very crop specific. It can range from very low TDS concentrations of about 450 milligrams per liter to very salt tolerant crops at over 6,000 milligrams per liter. So agriculture is obviously very crop specific. So TM3 described a lot of this analysis here of not only delineating our groundwater management zones, but computing our current ambient concentrations of TDS and nitrate, and then comparing it to some of the groundwater use thresholds that we identified in the TM. I also just wanted to make this point abundantly clear here about this deep aquifer system. And then as well as the groundwater uses and how much groundwater is being used across the Coachella Valley. We'll start here on the left here. About 57% of all groundwater pumped is pumped from the Indio West area, or the Indio West groundwater management zone. The color shading on these pie charts represent the groundwater model layer where this pumping is occurring. So this gray area represents layer 4. That's the deepest portion of the aquifer system. So the lion's share of the groundwater that is pumped in the Coachella Valley, as well as in the Indio West management area, comes from this deeper layer 4. The same is true in the Indio East area, where about 38% of all groundwater pumped in the Coachella Valley comes from this Indio East area. And again, most of the groundwater pumped comes from this deeper layer 4. A little different in Mission Creek. Mission Creek only accounts for about 5% of the total pumping in the Coachella Valley. But because the model that we use here has a very thick layer one, that most of the pumping comes from this layer. It's about 1,000 feet. Is that about right? About 1,000 feet thick for our layer one here in Mission Creek. And so this is more of a model artifact. Many of the wells in Mission Creek are deep. But because our layer one is so thick in the Mission Creek subbasin, that in that model, that most of the pumping from the model comes out of layer one there. And then again, Desert Hot Springs, a very small player in terms of pumped groundwater. A lot of it used for recreational purposes like hot springs. Okay. TM4, as I mentioned earlier, I'm not going to spend a whole lot of time on this because I'm going to talk about TM5, which is the actual model. But TM4, we basically published like, this is how we intend to construct these modeling tools to validate and verify that they are good enough for use to project TDS and nitrate concentrations. So we described all of that in the TM, got buy-in from the TAC, got buy-in from the public and the regional board, as well as our steering committee. This is the way we're going to go about performing our computer simulation modeling. And essentially what we used, and I think I have a graphic here, are the models that were generated, the groundwater flow models that were generated from the Sigma efforts for groundwater sustainability that is being required by the state. So we have two separate models, groundwater flow models, that have been developed by others, our TAC members, of the Mission Creek and Desert Hot Springs subbasin here outlined in black, and then of the Indio subbasin here outlined in red. We have a little blown up area right here, which shows you the grid cell spacing, size and spacing of these models. So each one of these grid cells is a model grid cell, and it's estimating how much water is in that grid cell and how that water is flowing to adjacent grid cells and how much recharge is occurring in each one of these grid cells. That's the spatial resolution of our groundwater flow models that we're using in our effort to simulate groundwater quality. So this is only groundwater flow. It's estimating volumes of groundwater that's recharging, volumes of groundwater that are flowing through the groundwater system. It doesn't estimate groundwater quality at all. We had to build water quality models on top of these models. That was our strategy that we documented in technical memorandum number 4. I'll pause here to take any questions you might have. I've been rambling on here for a minute. Well, I will continue on if you don't have questions, but please don't be shy. Okay, so in this task 5, and in our technical memorandum 5, which is now out for public review, we describe how we constructed these computer simulation models of water quality on top of the groundwater flow models. We validated that they work, and then we use those models to project a potential future under what we call the baseline scenario. I'll describe what that is here in a second. So again, these models we refer to them as water quality models, or sometimes solute transport models. They're based on a USGS publicly available code called MT3D. And so they sit on top of these groundwater flow models. And basically what we need to do is we need to assign TDS and nitrate concentrations to each one of our loading terms. Wherever salts and nutrients are being loaded, we need to assign TDS and nitrate concentrations, and then the flow models and the water quality models work together. The water quality can disperse, it can mix. There's certain parameters that we can control in these models to try to match our historical data that we have. So we run these models over a historical period in order to validate them, comparing our model results to measured data, and then we evaluate whether or not we think the match is good enough so that these models can be used to in projection mode to predict the future. The baseline scenario of the future is essentially the water supply and wastewater disposal plans of all the water and wastewater agencies in the basin. And those plans are now described in the groundwater sustainability plans of the agencies for the Mission Creek and Desert Hot Springs area and the Indio subbasin. So those are all described. They've been modeled with these groundwater flow models. And now it was our job to take that baseline and then add our water quality module on top of it to simulate what we think water quality will look like in the future. These big boxes here, this is just a graphic to describe our forecasting tool. These big boxes represent these two major models, the Mission Creek and Desert Hot Springs subbasin model and the Indio subbasin model. And water can spill from this area of the Coachella Valley underground. I say spill, but it occurs underground as subsurface flow from Mission Creek into the Indio subbasin model. So we have to attach these two groundwater flow models together in order to make the entire groundwater quality model work. These groundwater flow models have all these inputs: the mountain front recharge, stream bed percolation, artificial recharge of Colorado River water, wastewater percolation, septic returns, and irrigation return flows. These groundwater flow models simulate all of this volumetric loading of water to the groundwater basin. Our job was to assign TDS and nitrate concentrations to each one of these and how that might change over time, so that we could estimate how water quality might change in this part of the Coachella Valley groundwater basin. The models also simulate the export of water out of these groundwater basins through pumping or evapotranspiration, or in the case of nitrogen, nitrogen can undergo transformations into other forms of nitrogen. So we had to simulate all of that as well. The reason why these have different colors here is because the wastewater percolation, the septic returns, and the irrigation returns, what can happen is that you can have pumping that come out of the groundwater basin and then return to the groundwater basin through these different terms here. So you can set up a feedback cycle that needs to be simulated in these water quality models. So we made certain that this feedback cycle of pumping that then go to these recharge terms, that occurs in our groundwater models so that we can accurately simulate how salts and nutrients might accumulate due to these feedback cycles. It occurs in both the Mission Creek and Indio subbasins. So I'm showing it just with the same arrows here. And again, Mission Creek can affect Indio subbasins, so that's why we had to connect these models so that we could simulate that cascading effect of water and water quality between the two models. In terms of validation, again, we're going to look at our historical measured data and run the models over a historical period to try to validate whether or not we think these models are good enough to be used in a projection mode and predict the future. So the basic steps we went through here was, first of all, to We did a thorough review of the existing groundwater flow models, and then we modified them and connected them so that they would work together. And then we developed our water quality models on top of those groundwater flow models and developed all of our TDS and nitrogen inputs for our solute transport models. And then we ran them over this historical period of 2010 to 2020. This period was chosen because that's where our measured data was the richest, and we could do a good comparison over this 10-year period. And through that process, we did validate that we felt like the models were good enough to use for future projections. We sometimes had to go back and forth and look at the results, go back to our groundwater flow and our groundwater quality models, make some adjustments, and then rerun the models. So we did this in an iterative process until we came up with what we thought was a good match. Do we have a question? Okay, time check. I'm going to show you some of our historical results here. We got this x-axis is 2005 to 2025 here, and these are TDS concentrations from 0 to 2500. So these dots here represent our measured data, and then the blue line represents what the model was projected or simulating for the TDS concentration over this historical period, 2010 to 2020. So here you can see there's not much change going on at this well here that is located in the Mission Creek subbasin in the upper right-hand corner here. So, but we're matching that pretty consistent trend there. We would call that a good match. In this case here, we have our measured data in black dots that are showing some increasing trend for this well located down here in the Indio East management zone. And again, we're matching the magnitudes and then this upward trend here after 2015 towards some of the more recent data here. So we felt like this was a good match. But we didn't have good matches everywhere. This is another well in the Indio subbasin where we had a lot of historical data here, a data gap showing a little bit of an increasing trend where the model is certainly simulating an increasing trend, but it's increasing too fast compared to the model data. This is an area which we could probably improve in the future as we collect more data. And that is likely going to be one of our recommendations in the salt nutrient management plan to continue our monitoring program and then periodically use that monitoring data to go back and improve these water quality models over time. But we're still showing an increasing trend here. We're not matching the magnitudes very well, though, in this particular case. So we saw really good matches. We saw matches that weren't so great, but we felt that we're generally showing the right trends with this groundwater model. So we think that it's good enough to use. That's essentially my first bullet point here, that we can assess trends pretty well. Might not want to believe the exact model outputs in terms of the magnitudes of the TDS and nitrate concentrations, but hopefully that will improve over time through the use of monitoring data. So getting to our baseline, we selected a baseline that is going to simulate 2020 to 2070. And what we essentially did was we modified and reran the groundwater flow models for that baseline scenario, and then made all of our inputs for TDS and nitrate concentrations for all the loading sources. And then we developed our output, which would be TDS and nitrate concentrations by model layer across the entire Coachella Valley. We looked at ambient TDS concentrations by management zone, and then we looked at key wells, like you saw there, to take a look at at time series of TDS concentrations. Now, Carolina has promised to upload these animations to our website so that you can go through them. What we're looking at here is an animation of layer 4. So again, this deepest portion of the aquifer system across our entire model domain. And so what you're seeing here are the TDS concentrations shaded. Blue is very low TDS concentration, and then you get up to the yellows and oranges, which are higher concentrations. So you can see some of the effect of the recharge of Colorado River water here, down gradient of the Whitewater groundwater replenishment facility. You can see some of the influence of that recharge on TDS concentrations, as well as a lot of the overlying return flows from outdoor irrigation. You can see some of those areas as well. So one thing that we really we're already here at 2060 here. You haven't seen that much change. This is an extremely thick part of the aquifer system. It's the deepest part of the aquifer system. It changes very slowly. So groundwater basins change slowly in terms of their water quality. That's one of our observations out of this modeling exercise. But again, all these animations we will post to the website so that you can review them. The shallow aquifer systems, they will have more yellows and oranges on them. They are of higher TDS concentrations, and they will change more quickly too. You saw this time series chart here of the historical. Here we're showing you 2020 to 2070, and again, this increasing trend of water quality. All the key wells across the basin, we have these time history charts that we've published in the TM. We also looked at TDS concentrations in the municipal water supplies. So here we go to each individual municipal water supply agency and we volume weight all of their pumping in these model projections and for TDS concentrations and nitrate concentrations. So in this case here, we're looking at let's take the purple line here, which is the Desert Water Agency from their wells that are located in the Indio West Management Zone. And we're projecting what we think the TDS concentration might do over this period 2020 to 2070 here. And generally what we're seeing again are increasing TDS concentrations in most of the municipal water supplies across the basin. Generally, from a magnitude perspective, they stay relatively low, much less than 1,000 milligrams per liter, but they do all show generally increasing trends over time. And then we looked at ambient water quality concentrations for each one of the management zones. So here we're looking at the Indio East perched management zone and what we're projecting its concentration to do over time. This is the Indio East shallow, and then the Indio East deep and the Indio East west, again, the main pumped portions of the aquifer system, and showing these increasing trends, but generally staying below about 500 until you get out here towards the out years of the. So some of our main conclusions that we are projecting to see chronic increases in TDS concentrations in particular in the future. We think this is due to two main reasons. The mass loading from return flows from irrigation, outdoor irrigation, and then the mass loading from the artificial recharge of Colorado River water. And then an important component here is that this groundwater basin is generally closed, except for those agricultural drains. The water that comes into these groundwater basins stays there. It might get pumped out and then reapplied to the ground surface, but that closed nature of the groundwater basin causes salts and nutrients to accumulate over time. That's why we think, that's one of the main reasons why we think we're seeing increasing concentrations in these model simulations over time, is because of that closed nature of the groundwater basin, where we have minimal export of salts and nutrients over time. So our recommendations are to utilize these results from the baseline scenario, and develop new scenarios where we make attempts to manage the salt and nutrient loading. And we do this, don't take this in the wrong way, but we do this in a little bit of an unrealistic way. And why don't I just fast forward here to the scenarios where, for instance, golf courses, sorry guys, we're not going to remove all golf courses in the Coachella Valley, but we wanted to run such a scenario just to see what the relative impact of that would be. We did the same thing with all municipal outdoor irrigation, just to see what the relative impact of that would be. This may inform salt and nutrient management strategies. Like, what if we were to convert turf to native vegetation? What if we were to do that? How might that affect water quality in the basin? Well, we wanted to take it to the extreme here and test some of these scenarios out. So that is what we're doing in TM6 right now, is running some of these scenarios, learning as we run these scenarios, so that we can develop salt and nutrient management strategies that we will then again test with these models. So this is our first effort right now through these scenarios here. We're running one scenario where we're replacing all Colorado River water with, again, I told you earlier, about 600 to 700 milligrams per liter for TDS concentrations in Colorado River water. We're going to replace all of that in our model simulations with 250 part water to see what sort of effect that might have. That might be a totally unrealistic thing that could happen. We can't bring state water project and water into the groundwater basin unless we go to extreme lengths, and it might not even be feasible to do that. But we want to test out that scenario. Again, removing golf course irrigation, removing municipal irrigation, treating recycled water through desalination, and then again using that recycled water for percolation and for outdoor irrigation, seeing what sort of effect that might have. And then treating municipal groundwater. So what happens if the groundwater that's pumped gets treated through desalination and then distributed and used across the basin? You're certainly preserving the beneficial use of the groundwater, but it's also going to have a beneficial effect on the TDS concentration in the groundwater basin, because you're applying groundwater outside at a lower TDS concentration. So these are some of the scenarios we're running right now, and we intend to run more based on what we learn from these scenarios. I think I'm just about finished. Any questions on TM5? Slide 23.
I have a question, and it's on slide 23.
23.
Okay, so you got the TDS concentration to the left. You got one sample point where it's greater than 2,000, but it's not depicted to the right. At that sample point, is that due to irrigated lands or intrusion from the Salton Sea?
Can you repeat the question?
So the purple dot, it's a monitoring well that's being sampled from the Perch Aquifer.
Yeah.
Is that from irrigated lands or from intrusion from the Salton Sea?
Well, we did not do that sort of source evaluation on that. There might be somebody that knows that, that the answer to that question. But we have a couple of wells here. This is a USGS monitoring well that goes down to different depth intervals. And so that may well be water that's being drawn in from the Salton Sea. It's a very high concentration. So, and it comes, I believe, from a deeper portion of the aquifer system. So I think it indicates that it's coming in from beneath the Salton Sea, but we didn't do any sort of confirmation of that.
So if I'm looking at that data point where that is shows that it's greater than 2,000, it's not really impacting the deeper aquifer?
Well, first of all, we have some low concentrations in that area too that are within the deeper aquifer. So whenever we do these sorts of interpolations, we're more or less averaging all the available data. So it probably got blended with other lower TDS concentrations even at that particular point, as well as other nearby data of lower concentrations. So this process of interpolation is not perfect, but you're just trying to utilize the available data the best you can.
Okay, so I have a follow-up question to slide 25.
Which slide?
25.
25.
So in the notes that I wrote down here, you mentioned that you had 2,300 on the shallow perched zone,
Yes.
and then you have 643 in the shallow zone.
Yes.
So is there a barrier that is impeding there to be some sort of groundwater interaction?
Yes. Yes. There
And
is.
what is that?
It's not perfect. There's nothing that is absolutely impermeable. But first of all, you have the drains that are draining a lot of that poor quality water out to the storm channels and then out to the Salton Sea. But you also have very fine grained sediments generally in that depth interval of the aquifer system, which impedes the downward percolation of surface water and shallow groundwater.
That's all I have.
Okay. Is there another question?
It's right on the bank of stormwater channel as well, so there may be some flow that goes through there as well.
I knew there was somebody that knew more.
Do you want?
Sorry.
Sorry, I just wanted to point out that the data point in your question, Kim, comes from one of our nested wells that has a few monitoring intervals. So there's that aspect to it. There could come from that shallow interval from that nested cluster, but also it's that specific location is right on the stormwater channel as well. So there could be some influence or interaction from some of the water flow that comes through there. Could be, but just pointing that out.
Hi, Michael Placencia, Regional Board. I have a question regarding one of your scenario building bullet points presents treating recycled water through desal and treating municipal groundwater through desal. As a component of your scenario building, are you considering what the fate of the brine will be?
Well, I think the short answer is no. That is a central question to the feasibility of such a project on how you would deal with your brines. There's no way around that. Right now, we are just exploring the concept of desalination of groundwater or treated wastewater as a concept and just testing that out with our models. Does this make a noticeable difference in our trends of degradation going forward? And if it is identified as a preferred strategy in the future, then those would obviously be subsequent steps on evaluating the feasibility and the costs associated with doing such a thing. Joanne?
So Andy, just to follow up on that, would that be an evaluation under task 7? Because that will be the part where we characterize and compare costs. Would that sort of will surface at that time?
We would need to include some assumptions for brine disposal in the cost evaluation. I don't think we can go to the steps of fully evaluating the feasibility, but we would just need to make some cost assumptions so that it's a fair cost evaluation. We have a question online. Okay, so I think I've gone over this already, that this is the stage that we're at right now is running these scenarios and evaluating them with the models and gearing ourselves up for this economic analysis. What we will do from that point forward is that we will look at the effectiveness of these scenarios. We will look at their costs. We will compare and contrast, and we will try to come up with a scenario that is going to be the preferred scenario for managing salts and nutrients going forward. We may need to, as I was talking earlier about finalizing the management zones, it may be that we go back to the management zones and reconfigure them to best manage salts and nutrients going forward. And the thought is, at least this is the thought that was embedded in our work plan, is that we would be recommending TDS objectives for these management zones based on the California Water Code 13241 and performing the required anti-degradation analysis and then compiling everything into our final report. Those are our plans for the future. So for us, we'll be preparing this technical memorandum number 6, which is the forecast of the SNMP scenarios, and then TM7, the cost analysis. We'll be doing all that together. And for you, we appreciate your comments anytime. We'll accept them here verbally today in written format at any point in time. We've got our email address up here, our website. We do have a listserv. We are going to be having future workshops, and you are invited to submit comments on all of our draft TMs 6 and 7 that are the upcoming ones, and TM5 is out there for your review now. So when we get to the final report, that will have its own really extensive public review and public comment period associated with it. But that's what's upcoming. Am I missing anything, Carol? And again, I think this is our last slide, our website. But open it up for any discussion. Any further questions? Yes.
The upper state basins for the Colorado River, the upper state ones, you having any idea of what they could do maybe to keep some of the salt out of by the time we get it, or do we put it in ourselves? We don't, it's all part of the Colorado River.
Yeah. It's a really good question, because we have to assume TDS and nitrogen concentrations in the Colorado River water to perform our computer simulation modeling. We have to have some sort of projection for it. And so we do, right? What is it that we use? For the concentrations?
Salinity forum projections for TDS concentrations.
Yeah. And so in our TM5, I believe we've got a time series chart that shows what that assumption is for how the forum is estimating future concentrations will evolve in the Colorado River over time.
So they could do something to help eventually?
Yes. Yep, they're implementing their own salt nutrient management strategies upstream, yeah. Well, we'll stick around for questions afterwards if you want to chat anymore. Do you have any closing comments?
Violate my own ground rules. Just a thank you to everyone for joining us today and joining us over the last couple of years. And as we're moving towards the finish line, we hope that you stay engaged. We will stop this recording and get it posted up to the website in maybe a week or so. And all the resources and materials are there. The public comment period for TM5 is open until the 22nd, I believe, of July. And these are the folks working on it. So if you've got questions or you need clarification, we know how to get in touch. Thank you. Appreciate everybody.
Thank you.